what we are going to do now is we are going to take a look at a couple of definitions that are used for wall down and the shear flow or even free shear flow, but typically we will start with a wall bounded shear flow turbulent or laminar boundary layer. And the first one, we are looking into the displacement thickness. So we saw that the boundary layer thickness, so this is a boundary layer thickness. If you draw the boundary layer here, so this is a boundary layer. So we have the boundary layer thickness as a delta, symbol delta. This is a boundary layer thickness, and then but this is for uh, the we put the delta prime, then we call it this is as a displacement boundary layer displacement thickness like this. Actually, what we do here is what is the definition of this displacement thickness is we this can we can define this as a as a being the distance by which this solid boundary here. So we have a solid boundary here. So this solid boundary, we increase the solid boundary uh, about this displacement. So we increase about the delta displacement in order to provide the same d physics here. So we have a mass d physics for here, and then in order to get the same mass d physics, so we increase this boundary up to this height. So this also, now the area here is also mass d physics. So let we take a look what is the visual, and then we can see uh, what it is, and then we can see the mass deficit in the region here uh, where we have a lower velocity. And here we have a lower velocity due to the presence of the boundary layer. So because of boundary layer we have, and then what we'll need to do, we will need to increase the boundary layer thickness here in order to get the same amount here, delta star we get it. And then basically we just tick the boundaries due to the fact that we have a boundary layer present. And then so like here we have, then outside of what we would just have is a free stream velocity. So we have a free stream velocity here. So this is a free stream velocity. All right, and mathematically we can express the area for the mass deficits for the boundary layer here as this equation. So we have a integration from 0 to the delta rho u naught minus u dy, and then we have rho u naught the delta rho u naught delta star here in for this area. So this equation represent the area here, and then this equation will represent the area here. So if we can equal these two area, because we know that these two are same. So what we get is we have these equations. So this equation shows that rho u naught d that d star equal to rho integrate from 0 to delta u naught minus u dy. So if we take we consider we dealing now the flow, we dealing with external flow. So and we assume that it is incompressible flow. For the incompressible flow, we know that the rho is a constant, so we can cancel out this rho, and then we can bring up this as a denominator for these equations. So we have delta equal to integration from 0 to delta star, I mean, equal to 0 to delta 1 minus u divided by u naught dy. And then these equations, we call it a boundary layer displacement thickness, where here we displace the thickness of the boundary. All right, next another is quite common for the free shear flow or wall mounted shear flow. We are looking here is the boundary layer. In the boundary layer, is that momentum thickness. So the momentum thickness is a quantification. It is a quantification essentially of the amount of various activity that taking place within the shear flow, and it is a length scale. So this come out of the von Karman analysis, uh, where we already saw in it is a momentum thickness, which is we quote it as a symbol theta here. So the momentum thickness actually represent what the amount that the boundary layer need to move away from the wall in order to have the same amount of deficit that will occurs in the bound within this region. So if before this we said that it's a mass deficit, now we have a momentum deficit. So these amounts of momentum deficits due to the boundary layer effects, we can be translated by we increase, also we increase or we replace the boundary here up to this height. So similar way with displacement thickness. So in order to solve this problem, again we can equate, because we know that this area also the momentum deficits, and then we have these two equations, then we equate to this equation, can rewrite this equation. So we have rho u naught squared theta equal to rho integrate from 0 to delta u naught minus u dy. So again, for incompressible, we know that the density will be constants. So we can bring this u naught squared as a denominator for these equations. So you bring up here, you have u naught squared here. So, and then at the end of the day, we can solve this. We got this theta equal to from 0 to delta u divided by u naught 1 minus u divided by u naught dy. Then this equation we call it a momentum thickness. All right, so with that we already see the two boundary layers definitions beside the boundary layer thickness definition. So we have another two definition, which is we call it the momentum thickness and also the boundary layer displacement thickness. So these two equation will help us to in order to solve the boundary layer equation, boundary layer problem, especially in the laminar flow. Okay, and then here so next, we're going to look what is the we next to do for the equation. So after this, we will do for the boundary layer equations in order to determine the boundary layer based on the Navier-Stokes equations.